Hello? Oh, you can hear me. Okay, great. So good morning. Bonjour, tout le monde. I'm so thrilled to be here. I'd like to thank the organizers for giving me the opportunity to visit here and also to be here for tonight's match, which I'm hoping that I'll be watching with many of you here. Just to give you an idea of my age, I was here for the World Cup final in '98 in Nice. I was a teenager then, but just to give you an indication. So I'm really thrilled to be back in France for this big evening and the next week. Okay, so in the next 25 minutes or so, what I'd like to do is switch our attention a bit and focus on the multi-messenger astrophysics side, in particular with gravitational waves. So I hope to give you a broad overview as well as outline the challenges and opportunities that are coming up in the next decade or 2 decades. So in the last 10 years, we have now observed at least 390 compact object mergers. What I'm showing here on the y-axis is the masses and solar masses of the objects. The blue and the orange bubbles represent those black hole and neutron stars, respectively, that we have observed in gravitational waves. And you can compare these to the previously inferred black hole in pink and neutron star masses that were inferred from X-ray and radio observations. And so these detections, and of course, I'm just highlighting here our first binary black hole merger, GW150914. I'll be using this terminology which denote the dates of the detection, so the 14th of September 2015. And at the time, it was our most luminous source that we had observed in the universe. And these detections and analysis are taking place thanks to the two LIGO detectors, the Virgo detector, which I am associated with, as well as the Kagra detector in Japan. And within this worldwide network of detectors, we're eagerly awaiting the arrival of LIGO India. In particular, one of the big science drivers is really to do multi-messenger follow-up of these events. And just a brief reminder to make sure we're all on the same same page. What we're observing in gravitational waves is this H of T, this dimensionless gravitational wave strain. And in order to detect and actually extract information from the gravitational waves that we're measuring, we rely on these accurate models of the wave strain, which are called the gravitational waveform. They comprise 3 phases, the so-called in-spiral, the merger, the post-merger. And once we have these template banks and we're able to actually cross-correlate our detector strain with template banks of 10 to the 5, 10 to the 6 of these waves, predicted waveforms, we can actually not only detect the sources or the mergers, but also extract the following properties. So I'd really like to just highlight, this is the information that we are learning directly from the gravitational wave strain. These parameters here appear in the phase. We can track the phase very accurately for our low mass systems. And then these geometric properties, such as the luminosity distance, where they're happening in the sky, as well as the inclination angle, appear broadly speaking in the amplitude of the phase, and strong degeneracies can exist. And so one big challenge on the gravitational wave side as we increase the sensitivity of our detectors is to input more physics as well as potentially environmental effects into these waveforms. So returning back to this plot, there are a few things I'd like to stress. Number one, we're really uncovering a diversity in the fundamental properties of these compact objects and some highlighted results. We're able to now actually, with these 400 or so events, actually show that there's a structure in the mass distribution of these compact objects, which we believe are indicative of the formation mechanism, how these systems are forming. Several of you in the rooms are really experts on this. Secondly, we're able to say that the rate of the binary black hole merger appears to actually evolve as a function of redshift. And thirdly, on the more fundamental physics side, we're able to actually now test fundamental theorems, such as the no-hair theorem, as well as the Hawking area theorem. And this was really exemplified by our strongest binary black hole merger that we observed in January 2025, with a signal-to-noise ratio of about 80. And this allowed us, number one, to actually observe 2 distinct modes of the ring down, of what we call the ring down of the final remnant black hole. Okay, and by measuring these two distinct modes, we were able to actually then test the so-called no-hair theorem, the statement being that in the ring down, this actually comprises a superposition of the normal modes of the final remnant black hole. And within each mode, essentially the mass as well as the spin of the black hole is encoded into the characteristic damping time as well as the frequency. Okay, and so by measuring two distinct modes at 4 sigma, we were able to test the no-hair theorem, and then as well, because we were able to actually see the in-spiral merger and ring down with such a strong signal, we could actually also test Hawking's area theorem by comparing the progenitor masses to the final mass that we observed in the post-merger. Now, as this is the theme of this conference, and as has been sort of the focus of my research over the last 20 years, I'm going to focus on these neutron-star black hole mergers, where we expect in several of these instances there to be delayed matter outflows that are responsible for these electromagnetic signatures that we're seeing at different time scales and wavelengths. And this was exemplified, of course, by GW170817, which remains our first and only binary neutron star merger or gravitational wave merger that we have observed in every part of the electromagnetic spectrum, allowing us for this whole host of discoveries that I'll mention, as well as allowing us to actually pinpoint a gravitational wave merger in the sky. And we already had several discussions so far this morning about why this is the case, that this is our only one, but I'll return to it in my talk. And this neutron star merger is really impacting diverse fields in both physics as well as astronomy. And I'd really like to stress that this is really thanks to the thousands of people involved in the tremendous advances in the gravitational wave detectors, the time domain astronomy, as well as what is happening in computational astrophysics, as well as data theory. Oh, I forgot to start my clock. Okay, so let's go back to GW170817. And so the multi-messenger story really began in those first 2 seconds where the LIGO detectors observed and the Virgo saw a non-detection of this gravitational wave chirp that you're seeing in this time frequency spectrogram, and the Fermi and integral satellites observed a burst of short gamma rays 1.7 seconds later. Okay, and I will discuss what we were able to do with those first 2 seconds of observations. But when it comes to localization, we really depended on the gravitational wave detectors themselves. Yes, essentially using triangulation of the arrival times of the detectors in order to actually reconstruct the sky position, as well as provide some information, the 1 over distance in the wave strain, to where the source was. And so it was thanks to actually cross-matching the gravitational wave volume, which was sent out 5 hours after the event, with known galaxy catalogs, which allowed the majority of telescopes actually to observe this very bright blue flash in the galaxy NGC 4993 at 10.8 hours. And this was first detected by the SWOPE telescope in Las Campanas, but actually independent detections were made by several groups in that first hour because it was just so bright. Okay, and this really initiated, so it was 30 square degrees, the distance was 40 plus minus 10 megaparsecs, but this really initiated this unprecedented global ground and space-based effort, okay, with detections happening in the near-infrared at 12 hours, with the Gemini telescope. Swift saw the UV at 15 hours, and Chandra saw the X-rays at 9 hours, and the radio happening at 16 hours. And so this involved over 100 instruments, and this is indeed the paper where several of you also are co-authors, over 3,000 co-authors for those first 2 weeks of observations of this event, and indeed where I spent the majority of my time in that exciting period. And so one thing really just to stress was with this event, we really saw the importance of having on the ground northern southern hemisphere and longitudinal coverage, as well as large field of view or the ability to do galaxy pointing. And so what made this observation so beautiful was not just that we had this unprecedented amount of data, but that it broadly agreed with the two predictions that we've already heard about, the kilonova, this rapid neutron capture nucleosynthesis powered transient that's thermally emitting in the UVOIR, and really allowed, and I'm showing here the beautiful spectra from the ESO's VLT instrument that allowed us to demonstrate that these binary neutron star mergers are one of the astrophysical sites of our process elements. And as you've also heard, of course, this binary neutron star merger allowed us to actually confirm that they are the progenitors of short gamma ray bursts. And indeed, one of the many beautiful results that came out, I'd just like to highlight, are those that came from VLBI measurements at 2 different epochs, which allowed us, really remarkable insights into the structure of the jet, as well as actually having an independent measure of the inclination angle, which I'll return to its importance for cosmology. And so one big challenge is really modeling the outflow microphysics, as we've heard this morning, and some really beautiful work. I'm just going to quickly flash, I think, what Alex Brown in my group produced for me recently was a sort of literature review. So this is really in preparation, not complete, but essentially shows the different ejector masses with logarithmic scales from a whole host of different papers. And I really just would like to stress that there is still a lot of wide uncertainty. There is still a lot of debate, as we're hearing, about this, that even though this was our strongest event, and maybe will be our kind of golden binary for many decades to come, there still is a huge amount in terms of understanding the ejector properties of this event. And so there are still many open questions that we have not answered despite the amazing amount of observations. A few things I'd just like to stress in terms of the kind of science that we are able to do. So this, I hope this works. Very important, the ding. Okay, so in those first 2 seconds, we could actually constrain the speed of gravity to light to 1 part in 10 to the 15. The second big science result I'd like to stress combining these measurements was that we could actually constrain the neutron star equation of state. So neutron star mergers, and this is very interesting for high energy physicists, are allowing us this unique probe to the low temperature, high density region of the QCD phase, and it's hoped that these mergers, both the gravitational wave as well as the electromagnetic counterparts, will allow us actually to map out this transition between hadronic matter and quark gluon plasma. And what I'm showing here on the right was the contours produced by my then PhD student and being worked on in my group for the first 2 binary neutron star mergers seen in gravitational waves, the 1 kilonova plus 2 rotationally powered millisecond pulses. And you can see the 50 and 90% confidence regions shown in purple, with underplotted, the color lines are showing theoretical predictions of equations of state. Okay, and we have other works have shown that we need about 50 of these strong, and by strong I'm talking about a signal to noise ratio of 50 to really hone in on the equation of state. The third thing I'd like to mention is, of course, one of our basic endeavors is measuring the distances out to objects in order to actually map out the local expansion history. And so gravitational waves, we can measure the distance through the 1/distance dependence of the wave strain, and from the electromagnetic counterpart. In this case, it was the optical counterpart, but it could be also the radio counterpart. We have a measurement of the redshift. And so what you're seeing here is this GW plus the redshift observation in orange for our measurement of H0. And you can compare this to the then at the time, the CMB measurements at the high redshift universe shown in green, the 50-90% confidence region, and in the orange, these are the relative distance ladder measurements from the SHOES collaboration using Cepheids as well as supernova 1A, where currently there's about a 5.5, 6 sigma tension between these two sets. So of course, the hope is that gravitational waves will provide an independent measure of this H naught, and in particular bright standard sirens. And what you're seeing in blue is actually this combining the independent detection from the VLBI measurements I mentioned of the inclination angle, thereby actually breaking the degeneracy between distance and inclination angle that exists when we're measuring gravitational wave sources, especially at relatively low signal to noise ratio. We were able to actually improve this by work by Kenta Hotakazaka, led by Kenta Hotakazaka, by a factor of 2. And what we have shown is that we need about 50 of these GW plus redshift events to reach the 2%, which becomes interesting and competitive with current other distance measures. So one question that we've already touched upon and that I'd like to just quickly stress again, and I get asked a lot, is why have we not seen more multi-messenger mergers? And so the first thing really to stress is that from the public alerts, as well as the most recent catalog from the LIGO-Virgo-CAGRA collaboration, the empirical merger rate is much lower than was predicted originally in 2017 after GW 170817. But of course, notice the orders of magnitude uncertainty initially in 2017. Okay, so it seems that binary neutron star mergers are happening much lower than we initially expected with this kind of unicorn event of GW 170817. The second thing, and also work that Makenzie and I did over 10 years, 13, 14 years ago, Makenzie, was that, and when we were running simulations, was that it's not surprising that we're finding the majority of sources at thresholds. Indeed, they're much further out. This was exemplified by the second binary neutron star merger, which was 4 times further out than GW 170817. And this will continue to be a problem as we move forward. And so depth is really is important to, for electromagnetic follow-up. The other thing to stress is that a handful of neutron star mergers, particularly this one again, has only been detected with 1 gravitational wave detector. So we're looking at sky errors of thousands of square degrees compared to the 30 square degrees for the first event, as well as ensuring the accuracy and time of alerts and other astrophysical transients and variables. So in the interest of time, I will go very, very quickly because there will be an entire panel discussion, but really just to stress that it is not as bleak as I maybe have presented in the previous slide, because indeed there has been this new development where there have been several sub-solar mass candidates that have been released by the collaboration with relatively high false alarm rate, which may be potentially neutron star binary mergers, these subsolar mass, or indeed primordial binary black holes. And there have been 3 candidates proposed. And so indeed, these candidates are called superkilonova, and the entire panel will be discussing whether these could be the alternate sites of RPROS and indeed help reconcile the rates that we've already discussed that we are now coming into some issues. The other message just to stress moving forward is that we should expect a diversity of electromagnetic counterparts. We may also see early precursor emission, as well as, of course, moving, as we already heard today, beyond the standard paradigm of short GRBs and kilonova. And of course, you've heard this week, and you'll hear this afternoon from Fed Bianco's talk, is of course the amazing excitement in the last week that Rubin Observatory's LSST has actually began science operations, as well as SKA. These will all be operating now, today, as well as other facilities also with the DZA, this new German Center of Astrophysics that I will briefly touch on in my last slide. We are also participating in the exciting projects such as ZTF, as well as DSA in the future. And so in my On the astroparticle side, of course, there are many, many exciting things with CTA coming online, as you heard earlier this week, as well as potentially IceCube Gen 2, as well as for the early UV emission of kilonova. I'd really like to stress the advent of Ultrasat, as well as the UVX satellite that will be coming online. So my last 5 minutes, I just want to focus some time on what's happening on the gravitational wave side. So what I'm showing here is the timeline of our worldwide network of detectors, the LIGO Virgo CAGRA detector. We have finished the so-called fourth science run. The numbers here are showing the sky averaged orientation average distances for binary neutron star mergers at the end of this year, and really kind of motivated by Rubin Observatory's arrival. There will be this IR1, this intermediate run that will be operating for 6 months. And then in the at the end of this decade, we hope the fifth science run will run. There's a big question mark here with Virgo because new infrastructure, in particular to the stable recycling cavities, will have to be inputted. So it may not arrive till 2031 potentially. And then there is a lot of discussion, and that I've been working on in the last 5 years, is really building up the potential upgrades and science case for the current facilities, A-Sharp and Virgo Next, where we're talking about a factor of 2 increase in sensitivity. And of course, the real excitement is that we are also very much in discussion and activity to build the next generation of gravitational wave detectors. The Einstein telescope, which is European-led and which is envisioned to be a large laboratory 200 meters underground, either a single observatory with a triangular configuration, so 3 nested interferometers with 10-kilometer arms, or else 2L, 15 kilometers widely separated detectors. And the aim is that this detector will have a 10 times better design sensitivity, that's 10 cubed, in rate as well as numbers, and be a facility for the next 50 years. Currently, and very excitingly, there are 3 candidate sites to actually host the Einstein telescope, one in Sardinia, one in the Meuse-Rhine Euro region area, straddling the Netherlands, Belgium, and the western part of Germany, and one in Lusatia, in Saxony, where the design is either these 2 triangles or these 2L configurations. And the decision will be made next year in 2027. But I really would like to stress that it's not just the scientific community that's so excited about this project, but there's huge, huge political support from all the host nations. The one we're still waiting from is to hear back from Germany, okay? But there is real desire to host it. And here, just to give you an idea, this is a plot from Harsh Narula, AI generated, but you can see this is 1 day of observation that we expect for ET, okay? So just really, really transformative. On the US, there's the Cosmic Explorer Initiative. It's still a proposal where the aim is to have a 40 or 20 kilometer L-shaped observatory because there's much more land in the US. We can build 40 kilometer detectors, also to be operating as a global network with Einstein telescope. So my last few minutes, because this is really important, thank you, I really want to stress a few points, okay, about both Einstein telescope and Cosmic Explorer. Number one, what you're seeing here is the redshift range as a function of total binary mass. This is our typical signal to noise ratio threshold we are currently using. Again, I'm just using Cosmic Explorer as an example here, and you can put also the 100 and 1,000 signal to noise ratio. Okay, and we can overplot then our predicted binary neutron star mergers in yellow, neutron star black hole mergers in red, and binary black hole mergers in white, as well as overplot those known events that we know of until 2021. Okay, and the first thing I'd really like to mention, not just is the cosmic reach, but also, and these are the known GRBs in the yellow block, is just how strong things like GW17 or 817 would have been. We detected it with a signal-to-noise ratio of 32. If Cosmic Explorer and Einstein Telescope had been operating, it would have had a signal-to-noise ratio of 1700. Okay, and we're talking about distance errors instead of tens of percent or mass errors on tens of percent, you know, these really, really tiny events. So for events under signal to noise ratios of thousands, we can do precision physics and precision astrophysics below a signal to noise ratio of 100. And with this improved sensitivity of an order of magnitude of 10, we can also observe new populations of black holes, potentially those coming from population 3 black holes, population 3 stars, as well as those more speculative primordial black holes. And so we are really anticipating to see hundreds of thousands of binary neutron star and binary black hole mergers per year. And this, of course, brings a huge challenge both on the analysis side as well as on the theoretical side to actually make sure that we have accurate enough theoretical models, not only for the gravitational wave, but also for the electromagnetic counterpart. And so really just to stress that the excitement also for these high redshift sources is, of course, that they are potentially complementary and will provide really key information to how these heavy supermassive black hole mergers that we have observed and are observing, shown in red here with JWST, can actually form. What are the pathways or the seeds, whether they're low or high mass seeds, to actually produce also the supermassive black hole mergers that Lisa will be detecting, as well as those that we are currently detecting. So these are the kind of numbers we expect to detect. So I'm running out of time, so I'd just like to stress, if we look in the next 15 years, if we quickly say, okay, if I'm interested in nucleosynthesis, as we heard this morning, how far can we actually see with the future instruments on the ELT? We're talking about relatively close by, as well as to do cosmology, as well as demographics, where we need just the redshift. We can potentially go out to these kind of redshifts. So we're really just cherry picking the very, very bright golden binaries that we will see in gravitational waves with signal to noise ratios of 100. So I am going to end here. Please look at the blue book where you'll see really this treasure trove of science cases that are listed for the Einstein telescope, very similar also for Cosmic Explorer. And just the one last thing to mention, I don't know if many of you have actually heard about the new German Center for Astrophysics, but this is a center that I just joined last year. And the aim is to really build a scientific center of 1,000 people in the next decade that will unite research, innovation, and transformation. One of the big changes is actually to invest structural change in Lusatia, which is the center is being built in Gorlitz, which is our very most eastern point of Germany, bordering Poland, as well as very close to the Czech Republic. And so here are our 3 pillars, but really just to stress that on the scientific side, we are really investing a huge amount of resources as well as science and building up the science capabilities for these large infrastructures, SKAO, as well as the Einstein telescope. So I'll end here. Thank you.
Very nice overview, Tom. Okay, then just a few questions. Yep. Yeah.
Yeah, I saw that the LIGO GWTC5 report the binary neutron star merger rate is about 5 to 100 per gigapascal cube per year, which is already lower than the rate we estimate from the short gamma ray burst. Do you have any comment on that?
I'm just going to, so this is not updated for GWTC5, but essentially I think this is the comment that you're making, is that given the rate, this was where we were in 2017. This is kind of the latest rate that we're looking at, 5 to 120. Okay, it is becoming to be interesting, I think, for short GRBs, but I would caution that we should still not be too worried. I think it is important for understanding our process elements, and there does appear to be, I wouldn't say a tension yet, but there does seem to be, you know, something interesting happening there. But we also, I would like to stress, we did not have our gravitational wave detectors operating here or here. We heard this morning that there were several events that could actually be binary neutron star mergers, yes? And of course here we only have kind of 2 binary neutron star mergers, a handful of neutron star black holes, and this is the binary neutron star merger rate, yes? So given those 2 events, you know, it does seem to be low, but there are, you know, big gaps where there were interesting events that may also be binary neutron star mergers. They may also be collapsars, but, you know, I would say, yeah, just to bear that in mind.
So I'm not an expert, so pardon me if this is a naive question, but the factor of 20 change in the merger rate that you expect between 2017 and now, does that mean that there was an actual change in the physics of what we understand? And is it not possible to work forwards and simply say, I know what the massive star formation rate is as a function of redshift, therefore I can, and assume a binary, you know, a binary massive star formation rate, and work forward and say, well, this is what it should have been? That was my first question. Second question is if you can just make a comment on the space interferometers and their contribution in this field.
Yes, I'd be very, very happy to. You saw my backup slides. So. Yes, so basically for your first question, indeed, I think over several decades, there have been many people working on binary evolution, also now triples or multiple systems, looking at the predictions for how many mergers there should be, okay, per gigaparsec per cubed. And so this is really nicely, this is maybe a bit outdated now, but a review by Mandel and Brookgarden. And here you can basically see these are the triples and multiples. I'm sorry that the resolution is not great, but these are the predictions from binary evolution, yes? And so they really do vary by several orders of magnitude. And this is because of the large uncertainties at every step when we talk about binary evolution, be it mass transfer, stable or unstable mass transfer, the uncertainties when one of the systems goes supernova, neutron star kicks, and etc., as well as, of course, the common envelope. So, you know, they are still, as you can see, there really is a wide diversity in there. And so, you know, these are still in agreement, I would say, with this very, very low rate that we are seeing. But indeed, there are also the rate predictions that are coming from kilonova, as well as from short gamma ray bursts, as well as those from the galactic binary pulsar distribution extrapolating. And indeed, those are different probes to also get to this merger rate. But yeah, I would say that, you know, we only have 2 binary neutron star mergers that we have observed in gravitational waves. So, but it does seem low. I think we can say definitely that with some certainty.
Okay. Yeah,
do you want me to talk about Lisa?
Yeah, sorry, just time run now. So you can, discuss during lunch, surely. Yeah.
Okay, so yes, I will just put one slide up because I do think it is important. I think this has everything. Yes, and so of course in the millihertz regime, you know, we are expecting to see a whole host of a diversity of different types of sources. So be them galactic white dwarf binaries, which will essentially be monochromatic at the high frequency end. Several of them may be chirping 1 or 2 frequency bins. We also expect to see these supermassive black hole binary mergers. So here you can see the total mass. We'll see the in-spiral merger and ring down, and they can vary from a few hours to a year, depending on the mass that they'll be in band. And of course, we expect them to have electromagnetic signatures because these are in gas-rich environments, these supermassive binary black hole mergers. So these 2, we definitely expect there to be electromagnetic counterparts. There's also the kind of LIGO-Virgo sources that we would have seen, for instance, our first event 5.5 years before if Lisa had been operating, but at much lower signal to noise ratio. We expect 1 or 2 of these events, as well as MREs, these colored lines, which are basically compact objects going around a supermassive black hole. And these really allow you incredible precision physics in terms of testing the geodesy of the space-time itself. So you can really map out the space-time and really do fundamental physics tests. Okay. Thank you.
Yes, thank you again, Samaya. Very nice overview talk. I give you 3 minutes. Yeah. Okay. Oh.
Huh?
Idle phase. Okay.
You can go back on there. Okay, I just.
Okay, so next speaker is Makenzie Wortley, and time-resolved analysis of prompt emission spectra of bright Collapsar and Makenzie GRBs.
Thank you for, can you hear me okay? Okay, thank you for having me today. Yeah, I'm Makenzie Wortley, and I'm a second-year PhD student from the University of Birmingham, and I'm working with Ben Gompertz on gamma ray bursts. So I was thinking about how to introduce my research because that is quite a mouthful. And I realized that I work on long GRBs, which is ironic because I'm not actually that interested in collapsars. As uninterested as you can, I mean, you can't really be actively uninterested in anything astrophysical, I think, but I'm actually more interested in the search for kilonovae. So my work looks at how we can better know to look for them, because to find them, you really have to look. I mean, you have to be extremely lucky to just come across some. And it turns out that, as James said earlier, half of the spectroscopically confirmed kilonovae are from extended emission GRBs. So that's 1 out of 2. So first I'll talk about kind of I think of it as the old classification scheme, which is, not that there's a new one, but classifying gamma ray bursts based on their duration. So mergers were less than 2 seconds and collapsars longer than 2 seconds, which makes sense, right, from what we know about the nature of the progenitor. It makes sense with the emission timescales, the accretion timescales, I mean, because there's in general less mass available to accrete onto a black hole from a neutron star merger as there is from the collapse of a massive star. So we can use this when we see the prompt emission of gamma ray bursts to say where it's come from, right? But as we know, that's not the case from the observation of GRB 211211A. We know that actually mergers can last longer than 2 seconds. And so work by Ben and his team looked at a time-resolved spectral analysis of 211211A, and they fit the spectra to what's called the 2SBPL model, which is 2 smoothly broken power laws by Vera Rubin. And this model is actually a good analog for a synchrotron spectrum. So it has 3 power law slopes. Which one's the laser? This one. 3 power law slopes and 2 breaks, and those correspond to the E peak and E break in the model, and then the 3 slopes here. And at late times, the peak energy and the break energy seem to cross over. And this is actually the first time that the transition from fast cooling to slow cooling synchrotron emission was identified. So from here on, actually the band function is best fit, which only has 1 break because the breaks are not resolvable from each other. So this was very interesting, and we look also at work by Vera Rubin on the GRB 160625b, which is, I don't believe it has an associated supernova, but it's very much accepted to be from a collapsar. And she used the same 2SBPL model to look at the spectral evolution of this burst, and looking again at the E peak and E break, we can see that there's actually very little evolution and they both plateau. There's not much of a decay and they stay very separate. So we look at this and wonder if this could tell us anything about where the emission is coming from, because it doesn't really make a whole lot of sense for mergers to be able to emit for longer than 2 seconds. And really looking at this break evolution behavior, it looks very different, even though these are both technically long GRBs. So this is the motivation for my project, is to try and look into this further with a few more GRBs that we're pretty as confident as you can be of the progenitors. So I'll go through the sample that I've been using. So I'm looking at 3 collapsars. They all have associated supernovae, and they're all quite famous ones. You've probably heard of them already. So GRB 130427A, 171010A, and 190114C. And these are just rough light curves I've made from the C flux parameter from the spectral fitting, just to sort of show the general shape of the light curves. And so in my research, I'm using data from Fermi and Swift, because this is a bit of an archival study and they're publicly available. But going forward, having EPN SVOM is going to really help with this sort of analysis. So that's very exciting. And then the merger sample, we have 060614, 211211A, and 230307A. As spoken about earlier, there is no kilonova associated with 060614, but a supernova has been ruled out to very deep limits. It would have to be greater than 100 times fainter than other supernovae associated with gamma ray bursts. And there are also other things like there being negligible spectral lag for this burst and it having a large offset from its host galaxy. So we're quite confident that this one might be a merger. I appreciate I said quite confident and might in the same sentence, but you never really know with this sort of work. And then 211211A we've heard a lot about before, and 230307A I want to point out has a period of bad time intervals, just because it was such a bright burst. So in my work I've just excluded using this region for the moment. Okay, so this is the roundup. So these are all technically long bursts. They're all long GRBs. But we know that 3 of them are actually from mergers. And we don't want to miss the opportunity to find kilonovae because we think that all of these are from collapsars because they last longer than 2 seconds. So that's the idea. So now I'm going to talk about the method that I use for my spectral analysis. So the idea is to basically do as fine time binning as possible to really make the most of the very little data that we have. So I do a binning based on a signal to noise ratio. So if there's GBM data available for a burst, I take the dimmest sodium iodide detector and I bin that data by a signal to noise ratio of 50. And then I apply those time bins to the rest of the data available for that burst. So the other sodium iodide detectors, the appropriate bismuth germanate detectors, and then the BAT data, XRT data, LAT low energy data. And I've not used the high energy LAT data in this analysis, but it might be interesting to look into later. And then actually in the future, I hope to include some UVOT data where available as well. So this creates a lot of time bins. And for each time bin, there's a corresponding spectrum. And these I load into PyXspec using an automated pipeline that I've made, which cycles through each time slice and fits them to 5 different models. The first one being a simple power law, then the cutoff power law, then the band function, then the 2SBPL model, which I've spoken about already. And then I also do a fit to an additive band plus black body model to account for the possibility that actually the low synchrotron break is actually from a thermal component. So I'm trying to remain ambiguous about or allow for the possibility of there being thermal emission as well, not just assuming that it's a solely synchrotron emission, because to be honest, that's probably quite unlikely. I doubt it's that simple. So yeah, it's quite helpful having this pipeline because it makes it a lot easier to do a very finely time-resolved analysis and fit all of the models to the data without having to manually do it and it taking forever. And what's neat is once it's done a fit to one slice to the next chronological slice, it feeds in the best fit parameters from the previous slice as starting parameters for the next one, with some sort of guards in there to make sure it doesn't get stuck in a local minimum. So now this work is very much preliminary and I'm in the process of writing it up, but let's have a look at some results because that's fun. So I'll start with the two of the collapsars. So 130427A on the left and 171010A on the right. I'll talk about 130427A first. In the top, you can see how many time slices were made for each burst. So this one made 247 slices, and both of these bursts were best fit by the 2SBPL model. And so for 130427A, at least in this bright initial pulse complex, so it's photon index in the top, and then break energy on the bottom, log scale, and then the time, since the GBM trigger is along the x-axis in log scale as well. And then we have the different colors here in the background identifying what detectors had data for that time. So keep in mind the variation in band pass. So yeah, as I was saying, the first initial pulse complex fits well to a 2SBPL model and looks like it may be in the fast cooling synchrotron regime. And just other than some flux tracking behavior, both of the breaks seem to remain quite separate, which is interesting. But later on, there's a quiescent period of emission, and this is actually where the data is best fit by a power law model, which is in agreement with work by Makenzie et al. 2014. And then somewhat similarly for 171010A, we have the breaks remaining quite separate again. And what I would think would be fast cooling due to beta being above the slow cooling limit of 2.5. But it looks like actually both alpha 2 and beta are flux tracking. So this would be the two slopes either side of the peak energy in the synchrotron regime. So this would imply that they're both dependent on P. So I'm excited to look into this one a little bit more. But the fact that there are two separate breaks found is consistent with work by Chanda et al. 2019, so that's good. The final collapsar in the sample is 190114C, and I wanted to just go through this one just look at this one by itself, because work by Ravasio et al. In 2019 identified that it's likely that this burst actually enters, the afterglow comes into the afterglow rises quite early for this burst at around 4 seconds and peaks at 6 seconds. And you can kind of see that from where the way the fits just look completely different from around 6 seconds onwards. And this is actually best fit by band plus black body. But if we crudely overlay the light curve from the Swift Science Data Center, we can actually identify that there's this flaring here, which can't be from external emission and must imply some central engine activity. And if we isolate that, we can actually have a little look at what might still be going on with the prompt emission here, which is interesting. This is a bit of a cautionary tale as to how the afterglow can sort of mask what we can see from the prompt emission. So moving swiftly on to the mergers, we've got 060614. So this one only has Swift data, so a much narrower band pass. So it was best fit by the cutoff power law model, but I've included the band model as well, because actually when the XRT data comes in, it fits quite well to this model, and that's in agreement with Mangano et al. 2007. So it's likely that the synchrotron peak energy is between the BAT and XRT band passes, and then it travels through the XRT pass towards the end of emission. And then finally, hopefully I'm keeping to time, The last two mergers are 211211A, 230307A, and they're best fit by 2SBPL. So the findings with 211211A, we were able to get a lot more time bins and see some flux tracking behavior, but overall, it's in agreement with Gompertz et al. With the high break slowly decreasing to meet the low energy break. And for 230307A, it's really interesting because it appears that both energy breaks, so this one's linear scale because of the bad time interval, but both breaks seem to rise before the time interval and then decay quite rapidly at different rates afterwards. So this one's really interesting. So what to say about all this is it's very difficult to find a clear sign to differentiate between mergers and collapsars from their prompt emission alone. But I would say that there's a tentative suggestion here that perhaps during the T90 duration, for the collapsars, there's a lot less of a spectral evolution going on. And for the mergers, it seems like the decay of the synchrotron breaks seems to be a lot more apparent even before the end of the T90 period. So I'm excited to look into this more, and I'll put all of the results up in this very overwhelming slide to take some questions, but thank you for your attention.
Thank you very much, Makenzie. Nice talk. Okay, maybe 1, 2 quick questions? Anyone? Oh, okay. Maybe this way, yeah.
Thanks for a really nice talk. This is really cool. I've got possibly a technical question, which is, can you elaborate a bit more on how you're dealing with the different spectral resolutions and time resolutions of the different instruments in the same workflow? So is it different likelihoods for each instrument? And
could you be a little bit more specific? Sorry.
So, for example, you've got a lot of spectra of any one object, and they come from different instruments as a function of time. And sometimes they might have 2 instruments for the same particular time period. So how are you incorporating all of those things into your big fitting workflow? Is it 2 different likelihoods? What are you doing there?
So when I analyze each burst individually, so the spectra have been made just based on the sodium iodide signal to noise ratio, and then I apply those bins to the rest of them. So what sometimes happens actually with the bismuth germanate ones is because the signal isn't as strong, sometimes the net count rate later on in the emission is actually below 0. So for those, I just wouldn't use that detector for that specific slice. So I have some checks when I load into PyXspec as to what the net count rate is. And then for each spectrum from each instrument, I ignore stop me if I've misunderstood your question, by the way. For each detector, so there's an individual spectrum for each detector for each time slice for each GRB, and I ignore the relevant energy ranges, so like the 33 to 40 keV range for the sodium iodide GBM detectors, for example. And then they all have different fitting statistics, so like chi-squared for that data, that for GBM data. And then the way that I compare the different models is using the Akaike information criterion, and then also some physical interpretation too, because if, say, the band plus black body model fits equally well to the 2SBPL model, which happens quite a lot, but it says also that, say, the hydrogen absorption column, which I also include when there's XRT data, fluctuates all over the place. That's probably not physically realistic. Does that answer your question?
A little bit. I'll ask later.
Thanks. Thank you for the question.
I probably missed it, but I guess you have pinned the spectrum in using signal to noise ratio, right?
Sorry, could you?
You binned the spectrum based on this SNR, I guess.
Yes, yeah.
So do you see any kind of pattern between the intensity and the alpha value? So like over there, whether the alpha value follow the intensity or in the light curve or something like that.
So by alpha, do you mean the
spectral photon index of spectrum?
Yeah. So if I go back to the GIF, which I'm very happy worked, You can actually see the spectrum jumping around a lot. If you look that the intensity goes up, and then the spectrum sort of jumps up as well. This is in New Earth News Space, I should have said. So that's accounted for with the normalization parameter.
Okay.
If that didn't answer your question, you can find me as well.
Okay, maybe during
Yeah.
lunchtime. Okay, thank you very much again.
Thank you.
Dr. Leaf. The next question is, sorry, speaker is Mouad
Gnaoui.
Gnaoui. And the title is The Impact of Pair Production on Gamma Ray Burst Prompt Emission Spectra.
Yes, so thank you for having me. I'm Mouad. I'm a PhD student working at IAP in Paris, and I'm here to talk to you about my recent work on modeling the prompt emission of gamma ray bursts, specifically the impact of pair production on the GRB spectra. So let me start with a brief introduction. You know we see this plot every other presentation, so I'm going to assume you're familiar with most things in it, and I'll just stress that the model I'm working with assumes that the radiation comes from an optically thin part of the ejecta and that it comes from electrons. So pair production, as you probably know, is a process where photons above a threshold around 0.5 MeV in the rest frame can annihilate to produce pairs of electrons and positrons. This is known to produce a cutoff energy in the high parts of the spectrum. And when this is measured, it can be used to put a constraint on the bulk Lorentz factor of the emission region. Even when it's not, it can be used as a lower limit. Usually this is not seen, even in this, there it is. Even in this sample from a paper by Mary with 22 bursts that are detected in GBM and LATs, only 9 have this cutoff, while the others seem to have a tail that continues all the way to 100 MeV with no apparent change to the slope. But still, it's possible. However, when we produce pairs, these pairs are created with, and they carry energy equivalent to around the cutoff energy over 2. So they can be relativistic, and they can probably radiate in some cases. What we want to know is whether this radiation shows up, if there's any additional components in the spectrum that can arise from this, whether this stands out, if yes, where and under what conditions. There's also the exceptional case of the boat GRB 221009A, which I'm going to focus in the latter part of my presentation. So what is the model I've developed? It's basically a numerical model that solves precisely for the coupled evolution of leptons and photons in the emission region. This set emission region is assumed to be one zone, uniform and isotropic, and parameterized by these 5 parameters here in the rest frame. So I start with no photons and an electron distribution in the form of a power law with an initial density, minimum Lorentz factor, and an index. I need a magnetic field to tell me how important the synchrotron radiation is going to be, and a dynamical time to set the size of the region. The processes I'm taking into account are up here. And what I have here is a video that I'm going to start now. And you're going to see on the left the photons, and on the right the distribution of leptons. So immediately the power law starts to cool down, and as it does so, it radiates first a primary synchrotron emission and an inverse Compton component, synchrotron self-Compton. At the same time, some of the photons in high energy are annihilated, and they produce this dashed red line on the right that corresponds to the pairs that are being produced continuously in the region. This is a case where most of the high energy components here in Compton is absorbed, so we create many pairs, eventually more than they were initially, let me restart it maybe, eventually more than they were initially accelerated leptons in the region, and by that point they start to significantly impact the spectrum on the left. So we see, as it's going to come back in a moment, this low energy secondary synchrotron emission from the pairs that are being produced, and the high energy inverse Compton secondary component, mostly scattered over the primary synchrotron. At the very late times, once the leptons are no longer relativistic, you start to see this yellow component, which is the emission line, starts to peak from the spectrum. Here it shows up a little bit. over the continuum. So that's how the model works. Now let's do parameter space exploration. We use this grid. It's meant to be large and to well represent the bulk population of GRBs, mainly in terms of where the peak lands, their efficiency, and they're all optically thin for the primary photons. The big question is, what are the spectral components that are associated to pair production all across this parameter space? And the simple answer is that it's basically what I've showed you before in the example just above, but let's go over each component one by one. If you are in a region of the parameter space where inverse Compton scattering isn't very important, the cooling is dominated by the synchrotron process for primaries and also for the secondary pairs that are being created. And since you expect the secondary pairs to be produced at lower energies than the minimum Lorentz factor of the initially accelerated population, they will dominate at lower energies than the initial synchrotron peak. So this shows up as a potential extra break and a softening of the low energy index, which could appear in X-ray or optical. This is interesting because it's kind of a unique signature of abundant pair creation. Usually, you know that we expect and look for a break in the other direction, which can represent a transition from the fast cooling regime to the slow cooling regime, or even the self-absorption break. But this can explain an excess in this soft region of the spectrum. Usually it's not observed, and even when it's not observed, it can be used to put constraints on how important the pair production is in the spectrum. But there are a few cases of GRBs that have prompt emission that is very optically bright, and we are trying to see if they can be accounted for with this model. Another case in the parameter space is what you get when inverse Compton radiation is important. Then the primary leptons emit a high energy component here that can easily be absorbed by pair production. And then what you get instead is this energy gets reprocessed into this dotted red component, which is the secondary inverse Compton radiation. In these cases, you also expect the synchrotron to dominate at very low energy. So what you have is these low and high energy components that are coupled to each other because they come from the same source. But depending on the relative importance of these processes, the slope between the two can change quite a bit. And what we want to investigate is whether this can explain additional components that are used phenomenologically to fit sometimes that couple low and high energies. For example, here, when you have a band or a Comptonized components with a power law on top. These are all preliminary results, and there's still work to do before we can tell whether this works or not, but this is where I'm at. The final component is, of course, the annihilation line. It appears in the most compact cases where you really produce a lot of pairs and you annihilate most of them. In this case, you get this narrow emission around 0.5 MeV. Usually, the cutoff afterwards is very close to the line in order for it to really stand out. And the very important thing is that the pairs must cool down before they can annihilate. This is true because this is simply how the cross-section works. It falls down very rapidly with energy. So what I get is that every time the line stands out, it's often accompanied by this continuum that comes from the secondary inverse Compton, secondary pairs emitting an inverse Compton, usually at the same energies where the pair is produced. This component tends to drown out the line and make it harder to observe. And this will be the focus of the last part of my presentation, where I talk about both GRB 221009A and the emission line that appears in it. So let me first start by giving you a recap of the observations and how they went. Essentially, this burst was so bright that it allowed for truly exquisite time-resolved analysis of its spectral evolution. And at first, it looks like any other GRB with the standard band components. Then there's this bad time interval region where our detectors are saturated and we don't really know what's going on. And then afterwards, it's the same thing, but on top of it, we have this narrow emission line that seems to move with time. A really puzzling component that has only been detected for this burst. When you go and track the time evolution of the center of this line, you see that it's a power law with time with index -1. This is very fast, and it is compatible with what we call the high latitude emission scenario. I don't really have time to get into this, but it's important because it's the reason why we consider pair production annihilation as a potential candidate to explain this line, and a promising one at that. However, It turns out that it's really not easy to get a line that stands out from the continuum. What you need to understand is that the pair production and annihilation process, what it does is take some of the energy above the cutoff and reprocess it into the line. This is not very efficient if the cutoff is far away, because you can only keep the rest mass energy from your electrons to put into this line. And since the slope before the cutoff in most GRBs is usually decreasing, there's more energy in the continuum here than over there. In order to study this, we define a contrast. This is basically the value of the spectrum at the energy of the line over that of the continuum. So it's a number. The higher it is, the more the line stands out. And this is constrained to being at least a few, from 3 to 4 in the data of the boats, depending on at what time interval you look. And the question is, can we reproduce this with our one-zone emission model? Since I already have it computed on a grid, I can simply compute the contrast. And what I get, I summarize in this plot here. What you're looking at is on the x-axis is dynamical time, and the y-axis is the electron density. And the colors correspond to, for each couple of these parameters, it's the maximum over all other parameters of the contrast that you can get. So if you look at the top right corner, the brightest colors here, you get the maximum contrast all throughout the parameter space, which is something between 3 and 4, so barely compatible with the data. Other information is there's a huge part of the parameter space where you do not see the line. This is, of course, expected. The burst, the boat was a very unique burst, and we do expect to go to extreme regions of the parameter space in order to reproduce it. There's also these decreasing diagonals of similar behavior here, which correspond to constant values of the Thomson opacity, very closely linked to the pair production opacity. The only other thing that matters is where the peaks end up being. The cases that show the highest contrast are those that go all the way up there. They initially close to the optically thick limit, and since you create many pairs, most of them kind of go over the limit, and you get cases that look like this, where every photon that was above threshold is absorbed, is reprocessed into the continuum here and the line, and what you get is a very sharp cutoff immediately after the threshold, and this line that stands out with a contrast of around 3 to 4, barely compatible with the data, and is very importantly limited by this inverse Compton continuum here. So this is my conclusion slide, where I summarize the different ways that I found the pair production can show up in the spectrum, and where I stress how difficult it seems to be to reproduce the high contrast that we observe with the boats when you model the emission line and the continuum at the same time. A way to move away from this limitation and to get a higher contrast would be to somehow add a temporal dimension to your model. If you can separate the time where the pairs are produced and radiate with the time they annihilate, you can potentially get a much better contrast, and this is something I'm looking into at the moment. What we want to do to keep studying this is investigate how this model relates to specific bursts or population that would need to be very well parameterized in gamma rays, X-rays, optical, and high energies, which really emphasizes the importance of the creation of such a well-characterized sample to improve our understanding of GRB, the physical processes at play in GRBs in the future. Thank you for your attention.
Thank you very much, Mouad. Okay.
Yeah, for the both GRB MEV lines, if you want to use annihilation to explain it, you need Bonk Lorentz factor to be an order of 10. How can you do that for the boat in one zoom model?
I'm sorry, can you repeat?
The boat GRB, the MEV line is like 20 MEV. So if you want to explain it by annihilation, which is annihilating the moving frame by MEV, so you need order of 10
Absolutely.
for the Bonk Lorentz factor.
Yes, exactly. This is important. Thank you for the question. And it's what I did not have time to mention here. Essentially, the scenario is, since this emission here, this cooling of the line is very quick, and it's attributed to high energy latitude emission. So what you do is you follow how the line is evolving, and if you extrapolate that evolution, you find that it started somewhere during the bad time interval, which we would not have been able to measure it. And at that time, it would potentially have much higher energies. But as it as we exit this region, what we think we're seeing is emission from higher latitudes, which correspond to slower Lorentz factors, but the bulk of the ejecta, the gamma factor of the whole kind of spherical shell, is very much in the several hundreds and compatible with GRB prompt emission and dispersed.
So it's from high latitude, right?
Yes.
Okay, great.
Yes.
Any other? Yeah, that case, okay. So I understand your interest is line,
Yes.
basically. But yeah, I just wondered if you want to model secondary synchrophoton low energy component, and if only small fraction of electrons accelerated by shock,
Yes.
you have a thermal component.
Yes, absolutely.
Can we really distinguish? It's just only spectrum components around.
That's a very good question. It's something that I want to investigate next, in fact. But there's this case that's quite interesting, where it's dominated by synchrotron. And here, not only is only a small fraction of the electrons accelerated to produce this, but since you only get production here at the tail of the synchrotron emission, the amount of pairs that you produced is also very low. This plot here corresponds to this dot here. So it's not a very dense region, and you really create very few pairs, but still it's enough to kind of have this excess, which means that maybe it plays a role, and I do want to investigate how that relates to the thermal components and the thermal distribution of electrons, but that will be for next work.
Yep. Okay, thank you very much. Any other? If not, we'll move into next exciting. Okay, but before that, thank you very much.
Antonio, until what time can we go on?
We have
I would like to see the slides. Can you please you can just sit down. I think it's fine. Please. I can stay here so I can help with giving people the microphone. And if whoever is presenting wants to stand up, I think that would be a good idea.
So I have the link here to your. Copy this. Hope that this works.
Great. Thank you, Antonio.
Oh,
I can have it. How about I will just hand you the pointer whenever. Oh, you come here. Perfect. Okay. So welcome, everyone. We will have about half an hour session in which the topic will be observation of electromagnetic counterparts to subsolar mass mergers. We're very privileged to have 3 people in our panel, Professor Mansi Kasliwal, we have Sharan Salafia, and James Gillander, which will offer their personal perspective spanning from theory to observations. And our goal in this session is to see some of what has happened during previous follow-up of such events, but more importantly, let's focus on the future. What shall we do in the future theoretically and observationally to probe this science case? How can we even get subsolar mass compact objects? Not that trivial. Primordial black holes are primary candidates for such objects. And in fact, there is a very interesting possible connection with the nature of dark matter there. And when it comes to neutron stars, we know from observation of pulsars, they're typically observed and expected to lay pretty close to the Chandrasekhar limit. However, there are some channels such as, for example, disk fragmentation during a collapsar, that can lead to the formation of very light neutron stars. But how many of those events can we expect? How many have been observed? Well, so far, for what's been published officially by the LIGO, Virgo and Kagra collaborations, there are upper limits in the order of thousands to tens of thousands of events per gigaparsec per year, depending on the chirp mass. These searches were all done with a secondary, searching for a system with a secondary component that is typically between 0.1 to 0.2 solar masses all the way to 1 solar mass. And these events may have one subsolar mass compact object or both components be particularly light. There have been some candidates that have been released as public trigger by the LVK, some of which have been followed up and that our panelists will start talking about. So without further ado, I invite Mansi to give the first brief talk. I ask them to please keep their short presentations short, around 3 minutes, so that we have plenty of time for discussion.
All right. Good afternoon, everyone. So let me dive straight into the stirring up the excitement with the 3 candidates that have been proposed as candidate is very important, counterparts to subsolar mass mergers. The first subsolar mass merger was trigger in real time, came out on August 18th of last year, when Tomasa Umada called me and said, this is below our threshold. Our threshold is at 1 per year. This thing is 2 per year. But the probability that if this is real, then its subsolar mass is 100%. So should we go for it or not? I was at a party, but we decided, okay, why not? Let's have some fun. And much to all of our surprise, we actually have a candidate in that we cannot rule out, right? And this is a supernova, type 2b supernova, that early on just looked like something featureless, something actually with an unusual reddening, and something that later showed a radio detection as well. But except for these 2 clues, it's very, very unusual, like almost a magnitude, right? And G-I for a very short time, right? Not a normal thing that reddens for even at later times. But despite these 2 puzzling clues, in all other ways, this looked like an ordinary type 2b supernova. So is it associated or not? I mean, you can read our paper for the arguments for and against, but I think the jury is still out. And then a few months later, there was a second event, another subsolar mass merger. This time, the significance was better from LIGO. The real-time false alarm rate was 1 in 6 years. And once again, we found another type 2b supernova at the right place, right position, right time, right distance. But in all other ways, it just looked like one ordinary type 2b supernova in that error circle. So let's look at theory. Let's talk to Brian, who really wants to prove that primordial black holes is not the answer to subsolar mass mergers, but fragmentation is a good idea. And what fragmentation says is that you have, the Chandrasekhar mass limit goes as YE squared, the electron fraction square. So you can make subsolar mass neutron star mergers if after core collapse of a rapidly rotating star and a core collapse supernova from stripped envelope of any flavor, right? It could be 2B, 1B, 1C, 1C broad line. In the disk, you could have fragmentation, like gravity fragmentation, Toomri 1964 fragmentation. Again, nothing weird about the physics, right? I mean, you just fragment and form subsolar mass neutron star mergers. And if there are 2 that are close by, they could merge, give you a subsolar mass merger, and then they could merge with the central black hole as well. So you could have not one, but multiple such mergers in a very short time, right? So where's the neutron star black hole merger if this model is right? And surprisingly, again, right, just last month, there was another paper on arXiv by Brian Metzger and his postdoc Vishal Baibhav, which goes back to this event from 2019 that Igor had written a paper about. It's very, very high significance, very extreme neutron star black hole merger in which we had found this little line here of helium, which suggested it was some sort of type 1bc, probably old, but we didn't have very good constraints on the age. This was the light curve from the dark energy camera from Igor's paper. And what this paper here suggests is that this is actually a neutron star that was in an eccentric orbit around the black hole, also formed by fragmentation. Maybe there was a subsolar mass merge that created that somewhat massive neutron star. And that's now come into the black hole orbit and merged. And that's what we saw when we saw GW 190814. Again, very interesting. I wouldn't say definitive in any way. And even in the two events from which were type 2b supernovae, the newer events, the unfortunate thing is that LIGO, Virgo, the gravitational wave interferometers are not continuously on. So you see them on, off, on, off, on, off on the top here. And so you can use that to constrain that, well, we may have missed that neutron star black hole merger, and you can use that to constrain the formation radius and the black hole mass. And I am above my 3 minutes, so I'm not going to tell you the physics of it. But just say statistically, if you go read Xander Hall's paper, the statistical significance of these two events being associated is now at 4.9 sigma. And we're going to hear a lot more about that from Om, so I'm going to pass the microphone.
Makenzie.
All right, so, thank you. So pivoting away a bit more from the picture and sort of just dumping a bunch of data on top of you, I was responsible for leading the Pan-STARRS and Atlas follow-up project on the search for the counterpart to this first subsolar mass signal that Makenzie introduced. So this is just a quick summary of the data and what we had, and then we can try and fit this into what we expect. So on the left here are the SkyMap localizations for the GW signal. And on the top is the tiling from the Pan-STARRS telescopes, on the bottom with Atlas. Atlas is wider field of view, less deep, but north and southern hemispheres, so you're able to cover almost all of it. Pan-STARRS is restricted, of course, only to the northern hemisphere. We do this search, and we're able, from this search, to rule out a canonical kilonova like 17 GFO within about 10% of the total volume time parameter space. In addition to that, because we don't find anything interesting, we also take a bunch of data for this proposed candidate from ZTF 2025 ULZ. And here we just show that we don't think the data have any strong indication of being anything other than a canonical type 2b supernova. We find that in G, R, and I, the evolution of the shock cooling tail and the rise to the radioactive peak seem to match roughly what occurs within the class. There is some odd color evolution at early times, but perhaps this is some sampling effect, and the physics understood in the shock cooling tails is quite limited. And then this is just a panel on the bottom to compare the volumetric luminosity, temperature, and radius of this new object with a bunch of other type 2b's and the kilonova, and we see some divergence at quite early times. With regards to the second one, this one is potentially actually more interesting because although the sky map is larger, the sky area is larger, the distance is much lower, which means the volume to probe is much smaller. So you're able to, and because it's closer, you're able to probe better the limit for any kilonova emission. So here is just a plot from an upcoming paper from a PhD student in the group, Adam Smith, and this will hopefully be out soon. But this is just a plot to show what a canonical kilonova would look like and a canonical collapsar would look like in this region. And this just shows the coverage time from Pan-STARRS, Vera Rubin Observatory, and Atlas. So you can see that you would have probed most of the light curve evolution of these things with these three instruments. Note this is the Vera Rubin telescope, not LSST. LSST had not started, but they did trigger the TOO program to get some observations in the southern hemisphere for this object. And just to quickly say that actually, because this was much easier to follow up and it was much more local, with our observations, we can rule out a canonical kilonova within to 99%, around 99% precision within the 90% volume time. And you can rule out a collapsar in 100% of the volume time. Collapsar is the canonical association with this disk fragmentation model. There's now a suggestion that type 2b's are one of the drivers for this. The analysis for the type 2b or number of type 2b's in the volume is ongoing, but the collapsars can be ruled out, and so can. Thank you.
Thanks, James. Now, we'll conclude the talks before the discussion.
So I will just raise a couple of random points, and then I think let's leave space to the discussion. So one point was now touched by James briefly. So is the fragmentation scenario requires this collapsar progenitor, so a progenitor which is capable of forming an accretion disk. But in this context, we will also see after lunch it is pretty difficult to prevent then the system to produce a jet. And maybe this jet is not powerful enough to punch out of the star, but it's probably going to deposit some energy. And actually the properties of the 2Bs that have been potentially associated with these gravitational wave events do not seem to show evidence of any energy above what is normally associated to normal core collapse supernovae. So here we have the modeling of the supernova associated to the first of the events we have been talking about. And the ejecta mass is a few solar masses. The ejecta velocity is relatively normal, slow, and the kinetic energy in the ejecta, according to the modeling, is just about 1 FOE, so 10 to the 51 ergs. So this, I think, is one of the potential issues for this kind of scenario to be addressed. So are these supernovae compatible with the scenario itself? Then I wanted to just briefly touch on the chance association probability of these supernovae with the candidate gravitational wave events. Mansi did show some probabilities, but there is a very simple way to understand these chance association probabilities. So the volume of the search, so let's say the localization volume of the gravitational wave and the intersection of it with the part that has been covered by the surveys is about 10 to the 6 megaparsec cube. And this is true for actually both of the events we have been talking about. And the time distance of the supernova to the event is days. So if you just multiply this time volume by the rate of supernovae 2B, then you get in both cases a few percent up to maybe a 10% chance of having one supernova within this time volume. So indeed, it's interesting, just a few percent. So it's not really that you should expect it to happen often. On the other hand, we should also keep in mind that the gravitational wave alerts themselves are not very confident. For example, the first of the two, the 250818K, had a P astro, so a probability of being of astrophysical origin of only 30%, which means that in 70% of the universes, this was not a gravitational wave event. For the other event, S251112CM, the P astro was not given by the RBK because they do not actually release for subsolar mass events on a standard basis. But one can look at the relationship between the first run rate and the P astro for BNS events in the search that has triggered on this. And for the same force alarm rate, the P astro is about 50%. So probably also this one is not super confident as an actual gravitational wave event. So this is also something which we have to keep in mind. So it is super exciting, but the gravitational wave triggers themselves are not very, very secure. So still, I think the scenario itself of the collapse of disk fragmentation is an interesting one, which has to be studied more. And especially what we need is falsifiable predictions to be able to test with observations. I think the prediction of a gravitational wave from the merger of the subsolar mass merger remnant with the central black hole, this is an important prediction. Unfortunately, the duty cycle of LIGO did not help in this case. So I guess that this is going to be relatively easy to use in the future to falsify in a more lucky case. And then I think this is enough.
So, all right. So I guess just bits and pieces of takeaway. This is all very new. This means that some people are expert in it, but the experience still has to be built across years, simulations, and so on. So my encouragement to all of you is don't be shy, making comments, asking questions. Also, people in the panel is very, like, this is something so potentially groundbreaking, but there is still so much uncertainty. I think it's a great area to dare, starting maybe from this room. Talking offline with the panelists, we came up with a bunch of questions that then we then decided to kind of condensate in this one written here. What future follow-up should be prioritized for the next decade? Subsolar mass counterpart to prove or disprove the association with the gravitational wave event. First of all, we need confident gravitational wave events. I think that's something we can't escape, but these triggers will keep coming. So what do? Do we really sit back, not follow up? I really doubt that we will be lazy about it. But let me start asking maybe the theorists in the room, perhaps starting with Om and then opening the floor. What should we really expect in terms of observable? What should we as observers be after?
Maybe for the audience, it's completely clear. To me, was not. Since we talking about observables, is it clear to everyone what is this? You went very quick, so this is, I think, is the reason why to me was not clear. You are talking about supernovae 2, type 2, then you're talking about superkilonovae. For me, it's not clear what we are talking about. So can you please recap? Is it type 2? Is something else? Why is something else?
To expect. So what we're talking about is for a stripped envelope, rapidly rotating core collapse of a matter. Where during core collapse, the start of the black hole, and in the accretion, baby neutron star more subsolar mass. And so when these two merge, you get a supernova. And that's why it's sometimes referred to as a superkilonova. But the name is not important. The point is that there is the merger of subsolar mass neutron stars. More than one neutron star formed when the supernova collapsed. So this is a type 2b, which is a stripped envelope supernova flavor. Or a 1b or a 1c or a 1c broad line, any sort of thing where you have enough rotational kinetic energy. And that's why, as Om pointed out, right, the clue that there's radio emission to me is very important, right? I mean, that in one case, at least, we detect radio emission. The second case, data is still being analyzed. Because question is, I mean, do you see evidence of that extra rotational kinetic energy or not?
If I may comment on this, I'm not sure we can say solidly that these kind of events, as they are conceived, are going to yield any type of supernova. I think we have to predict what is the type of supernova. And as I was mentioning before, I believe that probably is not any type of supernova. Also because I guess almost everyone agrees on this, rapidly rotating progenitors are not very common. So I guess we should not expect any supernova to be produced in this scenario. Yet, this is not something which is clear. So maybe a normal type 2b can have inside all of this mess. The other thing that I would like to say is about the radio emission. So there have been radio observations of the supernova 2025 ULZ associated to the first of the events. At the beginning, these only showed emission from probably star formation in the host. Then later, there have been some detections of probably some variable emission. But this is absolutely on the level of a normal interacting supernova. So nothing very surprising for a normal type 2b supernova.
For a compact 2b, right? I mean, it's at the level of a compact 2b if you read the paper by Tanner or Dwyer. So it is consistent with the supernova with higher rotational kinetic energy.
I think this is also something that you can get easily from the ejecta shocking the circumstellar medium without any need for internal, for a central engine, let's say.
That's the question. What are the key observable? I see that there are three people in the audience who would like to make a contribution, starting from Matthias, sitting there in the center.
Yeah, so speaking about these possible observational tests, I mean, signatures. So obviously, I mean, you have this, if you have a kilonova within a supernova, you should be able somehow to see kilonova signature, like, and people have been doing this for like Collapsar, searching for our process signatures. So one thing that I think is different compared to those cases is that, I mean, we've seen this from James' talk, like this nice little movie with smiley neutron stars that merge and then they lead to a boring, let's say, a sad black hole. But in this case, the two neutron stars are pretty light, very likely. So they're not, regardless of the equational state, they might lead to another neutron star, a magnetar. And so I think possibly we would get a kilonova boosted from the magnetar. So the question, I don't think there are many predictions out there, but the question is whether we see some unusual behavior like in the supernova that we find, because the chance of finding a unrelated supernova are relatively high. But if you see some unusual supernova with some maybe magnetar, I mean, basically you will have two components. And so maybe this is something unusual, I don't know, photometric behavior on the rise of the supernova or the late times. No, we discussed this, so maybe you all.
Yes, I can comment on this, that if I understand the scenario correctly, so all of this happens within the core of a core collapse supernova. And around you have the ejecta of the supernova, and the diffusion time of this ejecta is much longer than the time scales, for example, of a kilonova. So most likely, in my view, anything that happens on these time scales is not going to be visible, unless the energy input is comparable to that of the explosion of the star. Also, this is not very clear, because if you merge two subsolar mass neutron stars, on one hand, I guess simulations are needed, because I'm not sure you form easily a magnetar, because these are very puffy objects, and they are going to be tidally disrupted a lot. So I don't know how much mass remains in the final object. Let's say that a neutron star protomagnetar forms, is going to merge with the central black hole in a time which is not very long. So I'm not sure it can form a magnetosphere and make spin down winds before all of that. So,
in the sense of looking at this from a modeler perspective, if we look at regular type 2Bs versus 1Bs, 1Cs, type 2Bs are definitely the lowest mass helium cores. So do we really expect these to be forming black holes, still explode, and still form a significant enough accretion disk to fragment into two subsolar mass neutron stars or more? Because what we would expect, if these are black hole forming stars, they should be more massive than 4, 5, 6 solar masses.
There is recent work by Adam Burrows and collaborators which shows that actually it's not mass that determines whether or not a star forms a black hole. It is actually other parameters like what happened to the star. I mean, you could have a very small difference in mass, like 15 solar masses versus 15.1 solar masses, and that changes whether a star forms a neutron star or a black hole. So I wouldn't use mass as a single parameter to form on determining whether a star forms a black hole.
But it's more, this supernova that you would get following it would be completely different, I would assume. If you form a black hole, how do you kick off enough material? Because if you take a 15 solar mass star and you form a neutron star versus 15.1 that forms a black hole, you'd be losing a ton of mass, I'm assuming. You're not going to eject the whole star. So surely there is some signature of this that we would be able to observe. And these are, if these look like completely regular type 2Bs, then either every type 2B is doing this, or we're missing something, and there's two formation channels for type 2Bs then.
Or it's a subset, right? I mean, from the 104 type 2Bs that we have from ZTF, nothing shows this unusual R minus I color evolution that ULZ showed, right? I mean, it's a magnitude compared to a tenth of a magnitude. It's not a small difference. And very early time data is actually not so easily available. So it is something could have been under our nose and we could have missed. Right. So I think it's important to keep an open mind here.
So we have 6 people with the hands up and 3 minutes left
just
for the discussion.
Yeah. Quick question is how much kilonova signature depending on neutron star masses? And this one is, let's say, chap mass is about sub 1, so maybe not different. But if fragments produce even smaller, in principle, 0.1 solar mass neutron star is possible. But according to that neutron star, actually it doesn't look like maybe diameter of maybe 200 kilometers, 300 kilometers, main part of crust and no liquid part. And it's going to be very different object. So this one is not particularly smaller, but just wondering, keep observing and subsolar, much smaller than solar scale, neutron star merger happened. What's the kilonova signal? Is it really kilonova look like? Or is it really observable in science, something enough out process material or energy outcome or that kind of thing? Just wondered.
James, do you want to take this?
Sure. I guess the quick and dirty answer is that actually this is very, very uncertain. The first order approximation is that it basically does something like 17 GFO, but on a much smaller scale. So you eject less material, it's less luminous, probably means it evolves more rapidly. But if these objects are happening nearby and we get good sky coverage, we can search for fast transients on these timescales. So we have ruled out something like 99% of the parameter space for a 17 GFO-like kilonova for the second one. If it's a magnitude fainter, like you might expect, then that number drops, but you just need to keep doing these high cadence deep surveys to identify this. But the first order, you're looking for something faint and fast and blue, probably.
Other than a supernova, which makes it really hard.
In the interest of time, we can take just one last quick question and then we can continue conversation over lunch and coffee breaks.
Okay, I try to just very quickly say, because it's a question or comment, maybe or actually also to Samaya, because I think in case of this disk fragmentation, if I understand correctly the scenario you have here, there is a strongly non-axisymmetric structure in this, like the whole thing, and similarly to the supernovae, magnetorotational supernovae, whatever, and also collapsars, this disk itself should be emitting gravitational waves, but at a lower frequency band. And we should look maybe into the future LISA data for broadband gravitational wave spectrum to confirm such scenario.
So I think in this scenario, what has been, let's say, covered in the literature is gravitational wave emission from the mergers of the clamps, which become compact objects and merge before merging with the central black hole, and then the mergers of the merger remnants with the central black hole. And all of this has been treated so far as if it were mergers in vacuum. Clearly they are not, and the effect of for example, mass accretion from the gas around on the waveforms has not been addressed yet. Also, actually on all the timescale, everything has been treated as like binaries in vacuum or tripoles. So I guess gravitational wave emission is one of the predictions that has to be brought to the next level if we want to be able to test it. Also, if we want to be able to search for them, because if they do not really look like normal in spirals, then it's going to be much more difficult to find them in the LIGO Virgo data.